We present residual learning from demonstration.
In this project, we were inspired by how well humans can acquire new skills. From an early age, we can effectively learn how to adapt our knowledge to environmental changes and how to account for model imperfections. So much so that we can get to use these skills throughout our daily lives in more than one setting. With this, we wanted to enable robots to be able to learn skills in a similar fashion. In this work, we focused on context-rich manipulation, and more precisely, we looked into learning the skill of insertion. We considered three different in complexity tasks to evaluate our work on. We looked into peg insertion, which is mostly dependent on the position of the robot and effector, gear insertion, which required precise orientation as well as a stronger push in downward direction, and LAN cable insertion, which required both precise position and orientation as well as very refined force control, for too much force could break the plastic tip. In this context, we wanted to address the following challenges. We were interested in being able to adapt to world changes, adapt to model imperfections, generalize to new settings, as well as learn safe and efficient policies. We propose to solve this by relying on learning from demonstration, where a robot hand is teleoperated by an expert demonstrator. We used DMPs, or dynamic movement primitives, to define a base policy extracted using a single demonstration. To recap, DMP split the task in two parts, a linear and a nonlinear one. The former can model the motion between 2 points following a straight line. The latter, parameterized by some parameters θ, handles the nonlinearities of a given demonstration. It is precisely those parameters θ that are being learned from demonstration. To account for orientations, we use a reformulated version of the previous equation that works in Quaternion space. The resulted base policy is then comprised by the two sub-policies. The outcome is what we call rote imitation that comes with some generalization properties. However, it cannot cope with slight environmental perturbations and task changes. For example, consider this second video where we perturb the start position of the robot. The policy fails to solve the task. To this end, we propose the following residual learning formulation. We define a concurrent adaptive policy which learns how to correct the learn from demonstration policy by relying on model-free reinforcement learning. It is trained using a sparse reward, and the adapted signal is passed to an impedance controller that commands the movement of the arm. However, applying corrections to different parts of the DMP formulation can lead to very different behaviors. Context-rich manipulations can benefit from local exploration along a nominal trajectory. Adapting in task space depicted in green in this figure gives us precisely this. Therefore, we propose the following residual learning from demonstration framework expressed in task space. In Cartesian policy space, we can describe residual learning using simple addition. This, however, cannot be done in the orientational policy case, for it is not commutative. Instead, we use Quaternion multiplication described in Schuster notation on this slide. However, quaternions are hypercomplex numbers, and learning a policy in such space can be very sample inefficient. Therefore, we define orientation-based residuals using a three-dimensional vector and a real number alpha, which can then be converted to a quaternion using the following approach. This allows us to efficiently learn an effective orientation-based policy. The full pose policy can then be expressed with these two formulations. We begin our evaluation in simulation where we defined an easy and a hard task, where the complexity was described by the size of the hole a peg is inserted in. We trained using only the easy task, but evaluated using both of them. Our results demonstrated that residual learning from demonstration performs a lot better than the alternatives while remaining more sample efficient. Upon examining the total amount of force experienced on the robot joints during an episode, we found out that residual learning from demonstration results in a lot less forceful solution, which makes this policy safer to run on a physical robot. We proceed our evaluation on the described before three insertion tasks. To recap, we consider three different in complexity tasks, and namely peg, gear, and LAN cable insertion. Our experiment considered learning a few different residual policies. Our results showed that policy extracted using model-free reinforcement learning were better than the considered baselines. In conclusion, we proposed the framework for residual learning from demonstration. We showed its capacity to adapt to world changes efficiently, adapt to model imperfections, generalize to new settings, as well as be safe to run on hardware. Thank you for your time.